All right, well, it's 11:03. Let's go ahead and get started. This is Chemistry 110. Make sure you're all in the right spot. I think I am. I'm Paul Young, and I will be your instructor for this semester. Little about me, I've been here at Triton for about 12 years, a little more. Before that, I was a full professor at UIC for 37 years. That's a long time. So I've been doing this for a long time. It also makes me slightly older than most of you. So if you have a question or you want to say something, speak up. I also don't walk real well right now, but I'm getting my knee replaced at the end of the semester, and hopefully that'll help. Any questions before we start? All right, today we are going to do Chapter 1. Going to do a very quick introduction first. Don't have a real office. 2 emails that work, P. Young at UIC or Paul Young at Triton.edu. If you have a question, send me something. Try your very best to be specific with your question. Don't say, I don't understand Chapter 5. That doesn't work. Try to be as specific as you possibly can. The textbooks. Officially, there are two, one by Trove. Not very good. I don't recommend it. Certainly don't buy it. This is my textbook. It's very good. I highly recommend it. We will follow the chapter sequence here in our lectures. It's available free on Blackboard. There are two websites you need to be aware of. chemistryonline.com, that's mine, and the Triton Blackboard site. All of our quizzes and all the material is going to reside on Blackboard. On Blackboard, you can also get the handouts for each of the chapters. Now, I attempted to send everybody a couple emails that had all of the handouts for Chapter 1 and the syllabus. They don't quite have Blackboard working well yet, so I had to try it twice, so you may have gotten two. But nonetheless, the nice thing about this is if you look, there are words on it. That means you don't have to write anything, right? There are also problems, but no answers. We will do problems in class, and what you're supposed to do is play along, fill in the answers, teaches you to write very, very small, but it's very useful as well. One thing that I would highly recommend you get is a scientific calculator. Now, they're really cheap these days. When I was a student, they were several $1,000s. They're not anymore, they're $10. The functions that you really need is going to be like x to the y, the log, 10 to the x, and that's about it. Calculator on your phone might work. The time to figure out that it doesn't work is not during the first exam. Okay? So play along. If it works, fine. If it doesn't, just spend the $10 and get one of these. The other thing you have to buy, which is sad, is a pair of goggles. Now, goggles make you look stupid. I know that. They're uncomfortable. I know that. But in my lifetime, I have managed to get chemicals and or glass in my eyes several times. And that's even worse than looking stupid. It is, trust me. So go to the bookstore, get a pair of goggles, check out the calculators. The course. Let's see. Class meetings, quizzes, exams shown in the syllabus. Questions will be drawn from assigned reading, what I say, and anything else I want to put on there. Basically, the exams are cumulative. That means it's everything you've learned since kindergarten, but I will do my very best to keep it current on what we've been talking about. We have two exams. I call them Exam 1 and Exam 2. We also have two quizzes, Quiz 1 and Quiz 2. They're given before the exams and they're online through Blackboard only. So make sure you're comfortable using Blackboard. The way the points break down, we have two exams at 100 each, two quizzes at 20 each, lab work is worth 100, final exam is 200. Now, I will be honest with you, I dislike final exams. I think they're not a teaching tool at all. It's a revenge mechanism, but nonetheless, there's a final exam, and the breakdown is basically 90, 80, 70. Any questions? All right. This is chemistryonline.com. Again, this is my site. A couple things that are current and useful. There is a full copy of the textbook here. You can, if you like pages, you can read easily. That's there. The chapter answers if you do problems. Tutorials are the link that you're going to be most interested in. These are a set of 35 or 40 algorithmic exercises. Now, the fact that they're algorithmic means that every time you click on new problem, you get new numbers, new everything, new answers, etc. I wrote these. That was heck, because great chemist, but programming, that was really tough. We'll talk about some of these. These are going to be very, very important during the class. Let's look at one of them. We start with a math review, then go down chapter by chapter. Exponents. Click on exponents. You get something like this. What it is, it's a problem. You click New Problem to get a new one if you don't like it. This is check answer once you put an answer in. And if you get it wrong and you want to see how to do it, show answer will show you for this individual problem. So, this is math review. Let's just look at this. This is a big number, 3.8 times 10 to the 8th, divided by 2.4 times 10 to the 20. Back in 8th grade, they were supposed to teach you how to deal with numbers with exponents. They may have, they might not have, but they should have. According to the 8th grade math, you would look at this and say it's division. First thing you do is subtract the exponents. 8 minus 20 minus 12. Second thing you would do is divide the coefficients. That's the 3.8 and the 2.4. Divide those, you get 1.6. And your answer would be 1.6 times 10 to the minus 12. All you want to enter here is the exponent only, so minus 12, and it says yes, you got it right. Now again, if you didn't get it right, you could click Show Answer, and this will show up. For this particular problem, it will give you the exact sequence of what to do. Kind of neat program. All right, why do I care about 8th grade math? Well, I don't, not at all. Today, if we were going to do this, we would simply punch this in our calculator and hit equals. This is my calculator. It's not as nice as yours, but it works, okay? Here's our problem. First thing I would do is I would type in 3.84. I'd find my exponential button, sometimes called EE. And then I would type in 8. So I get that. Hit divide. Then type in this guy. And then hit my equal sign. And by George, here's the answer. The reason this tutorial exists is not because I want you to do 8th grade math. I want you to learn to love your calculator. We will do big numbers like this all the time. Make sure you can do this again before the first exam. Any questions? All right, well then today we are slated to do Chapter 1, where we'll talk about basics and measurement. Atomic structure comes at the end of Chapter 1. Talks about orbitals, electrons, stuff like that. We'll actually do that next week in front of Chapter 2, because if we did it all, it would be a really long lecture. I don't take breaks. So if you're in the habit of drinking a gallon of something, sit close to the door. Otherwise, we're just going to go. We good with that? All right. Let's start off with matter. Matter is any substance that has mass. Now, remember, mass is different than weight. Weight is the effect of gravity on mass, but that's not important. Mass is an inherent and constant property of an object. Matter is composed of atoms. Atoms are composed of subatomic particles. They can be very small. Protons, electrons, and neutrons are the main ones. Protons are positive. Electrons are negative. If your chunk of matter, your atom, is going to be neutral, you must have the same number of positives and negatives. Neutrons are neutral, but they have to be there. Don't have to, but they usually are. Within the atom, protons and neutrons live in the nucleus, that's in the middle, and electrons are around it. So, everyone knows what an atom looks like, right? This was the logo for the Atomic Energy Commission in the 50s. And everybody assumed this is what an atom looks like. So we have a nucleus in the middle, protons and neutrons, and electrons going around in cute little orbits. The only problem with this description is that it's totally wrong. Totally wrong. First of all, electrons are not little balls in orbits. Quantum mechanics tells us that electrons form a cloud. And within this cloud, we really have no idea where the electron is. We can identify it to a region of space, but that's as close as we can get. So let's just do this to it. Electrons are in here somewhere. Okay? The other thing that's wrong is the nucleus. Typically, we show a very large nucleus. Everyone has seen Jimmy Neutron or Big Bang Theory. Yeah, that's what it looks like. No. Let's look at a rendition of a helium atom. Helium atom has 2 protons and 2 neutrons. I've used a grayscale here to represent the electron cloud. Within this, there are 2 electrons, somewhere. I have used a single pixel here to represent the nucleus. But we'll see in just a minute that even that is an exaggeration. Now, atoms are very, very small. If we had a copper penny, a single copper penny would have 28 sextillion copper atoms. That's a huge number. Now, this penny doesn't have 28 sextillion anything. This is a blank of zinc with a paper thin coating of copper. Yeah, that won't do 28 sextillion. If atoms are incredibly small, the things that make them up are even smaller. We have found a way to measure the mass of a proton. The mass of a proton is about 1.7 times 10 to the minus 24 grams. Now, that's this number in decimal format. Very, very, very small number. This representation is called exponential or scientific notation. This is decimal notation. We'll talk about converting one to the other, but the minus 24 here comes from the fact that we have to move this decimal 24 places to get it here between the 1 and the 6. We'll talk about how to do that in just a minute. A neutron is just about the same mass as a proton, again about 10 to the minus 24 grams. An atom or an electron is significantly less, about 10 to the minus 28 grams. All right, so they're very, very small. I said the nucleus that contains the protons and the neutrons was also very, very small. But the fact that these two together weigh so much more than the electron cloud means that virtually all of the mass of an atom is confined to the tiny little nucleus. Let's show that in pictures. Again, we're back to our helium atom. Single pixel, but that doesn't work. That's just way too big. This is the old Wrigley Field. That's some stage. This is a golf ball. So if our helium atom had the diameter of the entirety of Wrigley Field, the nucleus would be the size of a golf ball sitting on the infield. So not only is all the mass in this tiny little spot, but the atom is mostly empty space. Something to think about. Any questions? All right. Speaking of substances and matter, if we have a sample of matter, it contains only one type of atom. That's called an element. There are at least 118 known today. This is a periodic table. It doesn't show all of them, but they're there. Every element is identified by a chemical symbol. Now, quite often it's based on the name. For example, helium, which we talked about over here, is He. But there are ringers in there, based on Latin or Greek names for elements that were known in ancient times. Iron is not Ir, that's iridium. It's barium, symbol Fe. Now, chemists arrange these things in what's called the periodic table. This is one. On every exam, you will get a periodic table attached to your exam that will look pretty much like this. This is the shape of the periodic table. We will talk about exactly why it has this shape when we do orbitals at the start of Chapter 2. But this is what we have. Again, lots of symbols, lots of elements. Symbol ones go like this. Hydrogen is H, beryllium is Be, calcium Ca, carbon C, helium He. Magnesium kind of breaks the trends. It's not Ma, it's Mg. But okay, we can live with that, right? There are, like I said, ringers, however. Silver is Ag. Gold is Au, we just did it. Lead is Pb, 10Sn. Antimony is Sb somewhere. Here it is. These are very important. Sodium, Na. Potassium is a K. Copper is Co, that's cobalt. Copper is Cu. So sometimes it can get a bit confusing. Now, one thing I won't do is give you a blank periodic table and ask you to fill it in. I've seen people do that. I don't like that. Here's a list of, quote, starter elements and a guideline. When we talk about things in class, you kind of should know what we're talking about. So these guys are very common. We will do these. You will see them over and over again. Now, nonetheless, there are people that really like to know everything. And there are like sentences, my dear Aunt Sally ate something for dinner, whatever, where every letter stands for an element. You can memorize those if you want to know them all. Or I think it's much more fun to simply remember the song.
There's antimony, arsenic, aluminum, selenium, and hydrogen, and oxygen, and nitrogen, and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercury, molybdenum and magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium and cadmium and calcium and chromium and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
What do you guys say they're up to? 118 now. There was a day when I would stand in front of a class of 500 and I would sing that song. You're lucky. I'm not doing that anymore. All right, we said this is the periodic table. The first periodic table looked different. It was actually developed by Russian chemist Mendeleev in 1872. And, you know, he made some fundamental mistakes. He spelled table wrong. These are groups spelled out wrong too. But nonetheless, he got most of the elements in the right spot. And he did it simply based on reactivity. Well, as admirable as this is, instead, we use this one, the more modern approach. We have groups going across 1 through 8. Now, I know there are 10 elements here in the middle that are missing from our 1 to 8. Should be 18. But when we get to chapter 3 and talk about bonding, we'll see that doing the traditional thing, groups 1 to 8, makes understanding bonding much easier. Periods go down. These represent energy levels for the electrons. Again, next week. Let's just use our grid of groups and periods to do a couple very quick, simple problems. Group 1, period 4, what is it? Group 1, 1, 2, 3, 4, with K. Number K is potassium. Group 2, period 6. Group 2, 6, Ba. What do you reckon Ba is? Barium, exactly. Group 8, period 4, 8. Down, 1, 2, 3, 4, Ko. That's krypton. Not kryptonite, that was Superman. This is krypton. Any questions? All right. Every time we finish up a section, everyone sitting out here thinks to themselves, okay, what do I need to know for the test? I know you're thinking that, right? So what I do is after every little group, I will go to my collection of exams and I will pick out questions. So what you're going to see actually appeared on an exam. The symbols for copper, carbon, and cadmium are what? Well, we looked at copper. We said copper was not CO. It was cobalt. It was Cu. So we're down to the first three. Carbon, we saw carbon on our periodic table. It was simply a C. So we're down to these three. Now we didn't talk about cadmium, but we did say Ca was positive. Therefore, copper, carbon, and cadmium are those. Which element has two letters? Well, fluorine is F, phosphorus is P, oxygen is O, nitrogen is N, and silver, we said, was Ag. Na, everyone knows that by now, I'm sure. Not neon, that's Ne. Potassium is K. Ni, sodium, Na. For nitrate. Only one letter? Iron was Fe, antimony, Sb, 10Sn, sodium Na, phosphorus is just a P. And the last one, everybody knows now, potassium is what?
Okay.
Not Ka, it's simply K, kali. Any question? See how simple those are? You'll never see those on an exam. They're too simple. All right. Let's talk about the concept of an atomic symbol. The atomic symbol will have the number of protons in an atom. It'll have something called the mass number, which is the sum of protons and neutrons, and it'll have the symbol. This is carbon. Carbon has an atomic number of 6. That means it has 6 protons. It doesn't matter how many neutrons it has. Doesn't matter how many electrons it has. If you have an atom with 6 protons, it's a carbon. That's the atomic number. Periodic table is arranged by increasing atomic numbers. All right. The mass number is going to be the sum of the protons, that's the atomic number, and the neutrons in the nucleus. The atomic symbol is basically going to be the symbol of the element. The mass number is simply the sum of protons and neutrons, and the atomic number of protons, is shown as a subscript in front. So going back to our friend carbon, the most common form of carbon has 6 protons and 6 neutrons. The symbol, of course, is C. We would write the atomic symbol as carbon, superscript 12, subscript 6. Any questions? Pretty simple. Let's just do a few. Hydrogen, our symbol is H. Helium is He. Lithium is Li. Beryllium is Be. Well, hydrogen will start off with H. Number of protons, atomic number is 1. That's our subscript. Superscript is the sum of neutrons plus protons, and that's still 1. Lithium, atomic number is 3, symbol is Li. 3 goes in as our subscript. Our superscript is the sum of these two. 3 plus 4, I can do that, it's 7. Helium, symbol is He. Atomic number is 2, that's our subscript. Superscript, 2 plus 2 is 4. And finally, beryllium, symbol is Be. We have atomic number of 4, that's our subscript. Our superscript, 4 plus 5 is 9. Those were simple, especially with me doing them. Here, you do these guys. Our symbol is oxygen is O, carbon is C, potassium is K, iodine is an I. Quickly jot down the atomic symbols. Now I get impatient, so we'll talk about them as you do them, okay? Oxygen, our symbol is O. Our subscript is going to be 8. The superscript will be 16. Potassium next. Potassium is K. Our subscript is going to be 19. Our superscript is 19 plus 20. I believe that's 39-ish, right? Carbon, the symbol is C. Subscript is going to be 6. 6 plus 6 is 12 for our mass number. And finally, iodine. This one's higher math. Symbol is I. we have a subscript of 53. A superscript is 53 plus 74, which I believe is 127. Yes, without even using the calculator. Any questions? Now, I have given exam questions that were simply give me the atomic symbol for iodine. Okay, that's boring, right? This one was a little more interesting. Neutral element, 12 electrons, mass number 24. Well, the first thing you're supposed to do is sit and stare at it and say, what the heck is the element? The key is the word neutral. In order to be neutral, you must have the same number of positives and negatives. Now this has 12 electrons. That means it must have 12 protons. Therefore, it is magnesium. Okay, now we can do it. It's in what period? The periods go down, so it's in the third. What group? Group 2. How many neutrons? Well, if the mass number is 24, and 12 of them are protons, it have to be 12. And putting it all together into an atomic symbol, it would look like that. Any questions? Well, this brings us to the very first tutorial I wrote. I lovingly call it protons. Officially, it's an atomic configuration. Protons, electrons, and neutrons. You get a table with 6 spaces. With new problem, you get a different assortment. Okay? What you're supposed to do is you have 3, fill in the missing ones. Symbol is SN, that's 10. Take your periodic table and try your best to find 10. 10 is here. Atomic number is 50. That means 50 protons. The mass number is simply protons plus neutrons. 50 plus 66, 160. Number of electrons. Well, we have a charge shown here, a charge of +1. In order for this to be positive, it must have 1 more proton than it does electrons. So if it has 50 protons, it must have 49 electrons. Now that's fun, isn't it? You could sit and do that all day. You can. Bromine is our next one. Charge is -1, 44 neutrons. First task is finding bromine. It's over here in group 7. Go down. There it is. Atomic number 35. 35 protons. Mass number is going to be 35 plus 44. If our charge is -1, that means you have 1 extra electron. 1 more electron than you do proton. Therefore, for that 35, this is 36. This is so much fun. everybody's favorite element, uranium-235, is what you use to make bombs. Okay? When we hit chapter 11, I will explain to you in detail how to make one. Okay. Well, let's look for uranium. You can look all day, it's not there. Uranium is in this little group hanging at the bottom. We'll talk about why that's there in a minute. So uranium is here at 92. So 92 protons. Let's see. Charge. We have 92 protons, that's 92 pluses. We're given that we have 92 negatives. So this guy is a 0. Neutral. And finally, number of neutrons, 235 minus 92, 143. Now, you might just have so much fun doing these that after you get a bunch right, disappears. Email your instructor. Tell me just how well you did. It's exciting, right? You got them all. All you have to do is enter your Triton email here and click submit. It goes straight to my inbox. I used to do it that way. People would do these, they would send it to me, I'd add them up, and whatever. See how you were doing. But believe it or not, in virtually every class, there were 2, maybe 3 people that couldn't figure this out. They would put my email down here, they would put their mother's email in here, and it just didn't work. So when this finally shows up, there are people in the world that use this. It's used by lots of folks, but ignore it. Okay, just ignore it. Instead, once you're really comfortable doing these and you think they're neat, go to Blackboard. In Blackboard, you're looking for a folder called Tutorials 1. In there will be bunches of tutorials. These are actually little quizzes. Now on Blackboard, when you take a quiz, it can give you points. Every one of these is worth a total of 5 points. You can do these as often as you like. So here's the question. This is protons. You just fill these in. After you do 5, click submit, and you get a score. What is that score? Where do those 5 points go? They go straight towards exam number 1. That's right. This is extra credit. It is essentially added to exam number 1. Yes, this is an oh my goodness moment, because there are 15 of these. That's 75 points, even before you sit down to take the exam. You do these, you do them faithfully, I can guarantee you, you will ace this course. Any questions? All right, again, you're looking for tutorials 1. These are abbreviations. I think it gives you the full name from Chemistry Online. Wow. Okay, let's move onward. Let's talk about isotopes. I said once that it didn't matter how many neutrons you had or electrons. only thing that defines what an atom is the number of protons. So this is a rendition of carbon. Carbon typically has 6 protons, 6 neutrons. That's them. Again, you can't see it, but it's there. The electrons in carbon reside in 2 energy levels. We will do that a week from now. But that's why there are 2 energy levels shown. All right. The atomic symbol for carbon is this. What if we were to take this carbon and add an extra neutron? Like this. Well, now we have a carbon with a mass number of 13. Turns out with carbon you can easily do this twice, add another one, and get carbon 14. These are called isotopes. So all carbon, they just have different mass numbers. Now, okay, that's interesting. But what if you want to do quantitative chemistry? You want to weigh out carbon and know exactly how many carbon atoms you have. Well, you have a mixture of things that weigh different amounts. So that's a problem. Well, of course, we've solved the problem because chemistry can be very quantitative. We have found a way to figure out the natural abundance of the different isotopes here on Earth. Carbon is about over 99% carbon-12, about 1% carbon-13, and 14 is radioactive, and there's just a trace. So we can plug these numbers into an equation. This is the fraction, this is the mass, fraction, mass, multiplying together, we get slightly over 12, 12.01. If you look at the periodic table for carbon, right here, it is 12.01. You'll notice that virtually everything is it's not an even number. Oxygen is actually 15.9999. Fluorine is 18.9999. But nonetheless, they're all slightly different. Whenever you're doing quantitative chemistry and you need to know the mass, you look for the average mass on the periodic table. Now, speaking of the periodic table, the one that we've been looking at is nicely colored. Why is that? Well, these guys that are shown in this bluish purple color are all metals. They all have similar properties. They conduct electricity, they're malleable, not brittle. Over here, we have the yellow guys. These are nonmetals. Nonmetals are just the opposite. They are insulators, do not conduct electricity, and are brittle. Here at the junction between metals and nonmetals, we get our semimetals. These guys are semiconductors. They don't conduct usually, but you can apply a current to it and induce it to conduct electricity. That's how semiconductors are. These guys, groups 1 through 8, you will see these called representative elements in some textbooks. It's a very old term. These were originally thought to be the things that made up living things. That's wrong. You can find all of these too. These guys in the middle, the ones we ignore, are the transition metals. Their properties change smoothly from those of elements in group 2 to group 3. What are these doing down here? These are called inner transition metals. Well, actually, they don't go there. This row goes after lanthanum, this one after actinium. So you split your table open, move these up, and you get that. Now this is correct, but it's a terrible table. It doesn't fit on a sheet of paper. If you put it on a sheet of paper, you couldn't read anything. Nobody cares about these guys anyway. So we just shove them at the bottom, and we're good. When we get to Chapter 11 and do radioactivity, then we'll care about these.
I still just want to know why are those
Why? Well, they're mostly radioactive. They do not occur naturally. So even though it's a real element, you're talking maybe a 10,000th of a thousandth of a thousandth of a gram has ever been isolated. So we don't care. These guys over here, group 8, are called the inert gases. They're also called noble gases. They're notable because they do not react with anything easily. In Chapter 3, we'll understand why. Group 7, very important. Fluorine, chlorine, bromine, iodine. Very reactive. We use them all the time. Over here, group 1, alkali metals. Hydrogen, lithium, sodium, potassium, rubidium, cesium, and even francium. These guys all exist. The ones that are blue react instantly and even violently with water. Very reactive thing. Much less reactive, group 2, alkaline earths, beryllium, magnesium, calcium, strontium. Barium doesn't react with much of anything. Radium, killed Madame Curie. So, periodic tables come in many forms. This is one of my favorite odd forms. Just take it, wrap it around circles. We're not going to use this. So we'll use this on exams, etc. Let's look at some exam problems. Isotope of phosphorus, mass number 32, is used in radioactive medical treatments, okay? How many neutrons are in this isotope? This is what it looks like in the periodic table. We're looking for neutrons. Well, neutrons contribute to the mass number. Mass number is number of protons plus number of neutrons. We're given that the mass number is 32. Therefore, 32 minus 15, we have 17. Let's look at bromine. Bromine is here, Br. It's a halogen, group 7. Very reactive, very toxic. Atomic number is 35. That means it has 35 protons. It could also be the dreaded none of the above. So one of these or that. 44 neutrons. Well, 79 is the mass number. 35 minus 79 is 44. So that didn't help us much at all, did it? It's neutral. This is 35 positives. We must have 35 negatives. There it is. Any question? All right, let's move onward then to scientific notation. We said that this penny had roughly 28 sextillion atoms, and that the mass of a proton was this very, very small number. In order to make handling very large numbers and very small numbers easy, what we use is scientific or exponential notation as called. The number of atoms in a penny, 28 sextillion, 2.8 times 10 to the 22nd. We've seen the mass of a proton is 1.7 times 10 to the minus 24. Very, very large number, very, very small number. Writing a decimal number like either of these in scientific notation is actually fairly easy. What we're going to do is look at our number. We are going to find the decimal point. If the number has no decimal point, we'll pretend it does. And we will move this decimal point to between the first two digits. So we wind up with a number between 1 and 9. You count how many spaces you have to go to the left or to the right to do this. That will either give you a positive or a negative power of 10. Simple. 950,000. No decimal point, but we'll pretend that the decimal point is here. It's an implied decimal point. We will move it 1, 2, 3, 4, 5 places to between the 9 and the 5. So our first number, the coefficient, is simply 9.5. We were moving to the left. That's the hard part, figuring out right and left. We're moving to the left. So it's a positive. 5 places, 10 to the 5th. Any questions? I mean, that's simple. So tell you what, here's a list. Go ahead and rewrite each of these in scientific notation. Our first one, we have a real decimal point. We're going to move it between the 2 and the 5. So we get that. We will include all the numbers, but not the leading or trailing zeros. So 2.57. We had to move to the right to do that. That's a negative power of 10. We went 2 places, 10 to the minus 2. Our next one, we have a real decimal point again. We're going to move that real decimal point between the 1 and the 2. Write down all the digits. Now, we had to go to the left, 2 places, that's 10 squared. No decimal point. We're going to move the implied point between the 9 and the 3 and get that. Now, we had to move it to the left. 1, 2, 3, 4, 5, 6, 7. So that's 10 to the 7. Doesn't matter if it's plus or minus, the rules are the same. No decimal point, gonna move it between the 6 and the 5. And we moved it 1, 2, 3, 4 places to the left. That's a plus 4. And finally, real decimal point. Gonna move it between the 2 and the 7. We moved it 1, 2, 3, 4, 5, 6 places to the right, so it's a negative minus 6. Any questions? Well, let's see if we can do it backwards. Write these in decimal format. Now the right-left rules change here. So if we go to the right, it's positive, left is negative. We have 2.57. 10 squared is 100, isn't it? So just think of it that way. We're multiplying this by 100, we get 257. This guy is 10 to the minus 7. When you see a minus 7 like that, that means we're going to have 6 zeros in front. Then our decimal point. So let's move this over, put 6 zeros there, and you get this. Now mathematicians tell us that this is ugly format, okay? They don't like that. Just having a decimal hanging out there, so they say we should put a 0 in front. Doesn't count for anything, but it's there. Math is happy. 10 to the minus 4, so 3 zeros in front, then 1 for show. 658,000,000 times 10 to the 4th. This means we're going to move this decimal over to the right here 4 places. So 1, 2, 3, 4, it's right here. That's our number. Why do we do that? Why doesn't it work on anybody else? We will understand that when we do significant figures in just a few minutes. Finally, minus 1, just going to move it over in front of the 2, put another 0 there for housekeeping, and that's our number. Any questions? Let's go to tutorials and scientific and decimal notation. Click new problem, get a new problem. Check your answer, show answer. What you're going to do here is write the coefficient here. You will write the exponent here, If it's positive, do not use a plus sign. That's a general rule. Negative, you put it in. Positive, you don't. Our coefficient is going to be 8.3, isn't it? We are moving down by a decimal point. 1, 2, 3, 4, 5, 6, 7 places. So it's a plus 7. No plus sign. Our coefficient is going to be 4.6. We moved it to the left 2 places, so it's going to be a minus 2. We are going to have 7.1 here, 7.1. And we're going to have 6 zeros in front of it, plus 1 just for housekeeping. So we want 6 zeros, then 7.1, and that's it. Another one. Gonna have 5, 6 out here. We're gonna have 6 zeros after the 6, after the decimal point from here, and it's 56 milligrams. Last one. Six one is our coefficient. 1, 2, 3, 4, 5, 6 places, minus 6. Now, once you've done these and you're comfortable doing them, you are now going to go to Blackboard, right? And you're going to do the tutorial on Blackboard. Get your points. Don't blow them away. To write this number on Blackboard, you have to use what's called e-notation. So you don't do times 10, you simply do, for like 1700, 1.7 E3. We get 3 places. Now Blackboard has a sordid history of this. When Blackboard first came out, it only accepted a lowercase e. Then without telling anybody, 10 years later, they changed it to only accepting uppercase e. The latest version will take you to 1. I would do uppercase just to be safe. Any questions? 2 things I forgot to tell you about everything. Number 1, I forgot what it is. Let's do number 2 then. Number 1 was, when you're doing the tutorials on Blackboard, you have unlimited attempts. So if you sit there and you do it, and you get 3 points out of 5, simply click the button, do it again. You'll get different numbers every time. Not the same quiz, you get a different quiz. But over and over until you get your 5. Okay, you want your 5. Second thing I forgot to mention. As I stand up here and talk, I say lots of things, right? Sometimes I talk fast, too fast. Sometimes you think too slowly. I don't know. Some combination of the 2. Every word I say in class and all the slides are recorded. Okay? So at the end of class, probably by tomorrow, I have to process the video, move it to YouTube, put the link on Blackboard, and by George, you can sit and listen to the whole thing all over again. It's so exciting. Now, you don't get to see me, unfortunately, but all the content is there. Because it's YouTube, you can move the slider to the part that you don't get, and it makes it very simple. So, if you're going to have to miss class for any reason, it's there. Okay? But you don't want to miss the show, right? You'd rather be here. And if you have to miss, send me an email. All right, back to where we were. This next one is a little bit of a difficult section, but we're going to introduce a problem-solving approach that you're going to use for the rest of the semester. If you take general chemistry, it'll work through all of general chemistry, physics, and most of the rest of your life. It's a very simple problem-solving algorithm, and we're going to do it. Well, let's start off talking about the metric system. Length. Standard unit is the meter. That's abbreviated with an M. 1/100th of a meter is called a centimeter. Mass is a kilogram. Kilo stands for 1,000. 1/1000th of a kilogram is a gram. Cubic meter for volume. Cubic centimeter is what we will typically use. That is something called a milliliter. That's exactly the same volume. Cubic centimeter, all that stands for is simply a cube. It's 1 centimeter on the side. If you're measuring a solid, quite often you will measure its volume in cubic centimeters. If you're measuring a liquid in chemistry, you'll use something called a milliliter. A little m here is milli. It's 10 to the minus 3 is the multiplier. And it's exactly equal to 1 cubic centimeter. All right, let's talk about these multiplier things. In the metric system, we use these little letters to abbreviate a multiplier. M represents 10 to the minus 3. So when we had a milliliter, that was 10 to the minus 3 liters. Let's focus on this. The letter M stands for 10 to the minus 3. If we're dealing with meters, and we have 10 to the minus 3 meters, we can write that shorthand as 1 milliliter. M is the 10 to the minus 3. Makes it nice and quick and easy. We can also set this up as a ratio. The ratio would look like this. We're relating meters and milliliters. So we could say 1 millimeter is what? Well, the M stands for 10 to the minus 3. So 1 millimeter is the same as 10 to the minus 3 meters. That's all it is. Simple as it can be. Ratios are what we're going to be using because they fit into our algorithm. So, when we're interconverting metric measurements, we're going to use simple ratios or proportions to do that. If we were relating millimeters and meters, again, we know that milli is 10 to the minus 3. So we could write one ratio. A millimeter is the same as 10 to the minus 3 meters. The M is simply 10 to the minus 3. We could also say, if we had a meter, that would be 1,000 millimeters. Now, why does that work? Well, remember, M is 10 to the minus 3. So 10 to the third multiplied by 10 to the minus 3 is 1. So this is 1, that's 1. In fact, both of these ratios are simply 1. Because they're 1, We can write them like this, or we can simply turn them over. It's legal. It's a 1. All these are equal to 1. So for every conversion, every relationship, we can have 4 possible ratios. Let's just practice that a little bit. Picometers and meters. First thing you have to do is know your prefixes. Pico is 10 to the minus 12. So 1 picometer is 10 to the minus 12 meters. And picometer, pico is 10 to the minus 12 meters. We can also say if we had 10 to the 12th picometers, we would have a meter. Let's do it again. Micrometers. Greek symbol mu stands for 10 to the minus 6. So, micrometer. 1 micrometer, 10 to the minus 6 meters. If we had 10 to the 6 micrometers, we would have a meter. One more. Nano. Nano is easy to remember because it's 9. 10 to the minus 9. 10 to the minus 9 meters is 1 nanometer. 1 nanometer, 10 to the minus 9 meters. We could also say if we had 10 to the 9 nanometers, we would have 1 meter. Now down here, we have some that used to be very foreign to people. Kilo is 1,000, mega is 1,000,000, giga is 10 to the 9th, a billion. We do never use these units now. Any question? All right, you're all sitting there wondering, what is this algorithm? Basically, it's given, ratio, and time. You look at a problem, a word problem. In there will be a number that's given. The number will have units. The rule is that whatever units you have are given must be in the denominator of a ratio. Your problem will also tell you what you're trying to find, and it will have units. Those units are going to be in the numerator. So, if we were given meters and wanted to find kilometers, our given is meter, so meters is in the denominator. We're trying to find kilometers, it's in the numerator. And we would simply multiply the given number by this ratio. Do a real problem. If I tell you we have 6,000 kilometers, how many meters is that? Our given is going to be our 6,000 kilometers. The ratio must relate kilometers and meters, and kilometers must be in the denominator. And we're trying to find meters. That's the numerator. So we set up the problem just like this. Our given. Here's our ratio with kilometers in the denominator. And we're trying to find meters. Kilometers will cancel. 6,000 times 1,000, we get 10 to the 6th. I am serious when I say we will use this given ratio find algorithm all through the course. You can use it all through general chemistry, physics, etc. It's the answer to everything. Let's go ahead and look at some simple ratios that we could stick in conversions. If I give you 2,000 grams and I want kilograms, what do? This is our given. The ratio must have grams in the denominator. Kilo is 1,000. That must be in our numerator. This is the ratio that works. Kilograms, grams, kilograms, grams. Multiply the given by the ratio, and we get 2 kilograms. Meters and micrometers. Meters is going to be in our denominator. Micrometer in the numerator. Micro is 10 to the minus 6, isn't it? 1 micrometer, 10 to the minus 6 meters. Multiply the given, 10 to the minus 7 meters, times this ratio, we get 0.125. See why you want to be able to do this quickly on your calculator? Yeah, these are real problems. 10 to the minus 4 grams is nanograms. Nano, we said, was 10 to the minus 9. Grams, nanograms, grams, nanograms, and 10 to the minus 9. Simply multiply this by that, and we get 10 to the 5th nanograms. Meters, kilometers, kilo is 1,000. Meters in the denominator, that's our numerator. 1,000 meters and 1 kilometer. Simply multiply this by that, we get 65.8. And finally, grams and milligrams, well, we've done that. That's simple. Grams in the denominator, milligrams in the numerator. Milli is 10 to the minus 3. Multiply this by that, and we're at 278. Any questions? All right. Most of these tutorials I wrote when I was at UIC. Taught classes of 500 people, 2 sections. A lot of people. It's different here. I never wrote a metric conversion. A couple of years ago, some people in the class said, would you please? So I did. So this is the newest one. Convert 3.04 grams to kilograms. Okay, our given here is 3.04. We're trying to find kilograms. The ratio must have grams in the denominator and look like this. Again, this is 10 to the minus 3 times 10 to the third. That's 1. And that gives us 1 gram over 1 gram. Our given multiplied by the ratio looks like this. Grams will cancel. And we get over 3. If you hit show answer, something like this will show. One more. Milliliters and liters. Again, milli is 10 to the minus 3. So this is 1,000 of a liter. Liter is what we measure things in if they're liquid. So this is 1,000. It's the same as a cubic centimeter. Same volume. So, our given going to be our 2510 mils. Milli is 10 to the minus 3, there it is. And we're trying to find liters, there it is. 10 to the minus 3 liters is 1 milliliter, also 1 cubic centimeter. So, is our given? Here's our ratio, milliliters cancel, and we get 2.5. Now again, when you go to Blackboard, the notation, 10 to the 2.4 times 10 to the minus 3 would be 2.4 e minus 3. Just remember that. One last thing in metrics that we could do now is temperature. We all know 32 degrees is cold as the water freezes, boils at 212. Well, it doesn't in chemistry lab, okay? Chemistry lab, we use centigrade. Water freezes at 0 degrees and boils at 100. There's one other measuring scale that we will use in Chapter 9, called Kelvin. Kelvin differs from centigrade. We'll never use Fahrenheit. Never, I promise you. Kelvin differs because water freezes at 273.15 and boils at 375. It's a useful scale because here there's 100 little dips. Here, there's still 100 little dips. We'll see why we have to use this, though, in Chapter 9. All right, our last subject for today. That ought to make you happy. Makes me happy. Significant figures. If I just give you a number, say I measure this tabletop and I give you a number, you can look at me and say, okay, how accurate is that measurement? Significant figures will tell you that right away. Let's say we have a scale and an arrow. The arrow is pointing down here. Okay, this is 50. 1, 2, 3, 4, and 5. Well, the arrow is between 50.4 and 50, or 54 and 55. Somewhere in there, right? So, what is it? Well, as I look at it, it's darn near halfway between them, right? So, I could call this 54.5 and feel comfortable. The 54 I know about, but 0.5 is my best guess. Now, if I were to say it was 54, you say, well, that's wrong. It's more than that. If I said it was 54.666666667, you would say that's stupid. You don't know that. You know it's somewhere between 4 and 5, about halfway. This number has 3 significant figures. The last digit, this one, is your best guess. We're sure of everything in front. The last digit is your best guess. Simple. Most people get that just as a concept in measurement. Only place that people have difficulty with this is when it comes to zeros and calculations. So let's look at zeros. Let's look at 2 different types of numbers. Numbers with a decimal point and without. With a decimal point, leading zeros, that's zeros in front of the real numbers, are never real. They're never significant. They're gone. everything after you do real digits is real. Here, 0 was the best guess. This is called a trailing 0. Again, it's best guess. If we don't have a decimal point, the trailing zeros, these guys, don't count at all. The best guess here was 2. If we have zeros in between real digits, they always count. So, let's look at this again. Here's our first one. This is 10 to the minus 1, 2, 3, 4. 10 to the minus 4. 1 times 10 to the minus 4. It does have a decimal point. That means these leading zeros go away. This is a trailing 0. It's real. This number has 2 significant figures. $3,400, no decimal point. Trailing zeros don't count. We're left with 2 digits, 2 significant figures. Do one more. 2 more. 3 more. I don't know. We have a decimal point. Leading zeros go away. This 0 is in between real digits. It counts. We have 3 significant figures. $20.50. No decimal. Trailing 0 doesn't count. This is between real digits. 3 significant figures. And finally, what if I gave you 6.02 times 10 to the 23rd? Well, what's the decimal equivalent of that? It would look like this. No decimal point. These are all trailing zeros. This one's in between real digits, but these all go. And we're left with 3 significant figures. Whenever you do scientific notation, all of the digits that are significant are in the coefficient. Power of 10 is not significant. So whenever you see scientific notation, all of these are real. Let's do 2 things at once here. Write these in scientific notation with the proper number of significant figures. I will pause for a moment. Our first one, we have a real decimal point. Leading zeros aren't going to count. We're going to have 3 significant figures. To get scientific notation, we're going to have to move this to the right 2 places, 2.5 times 10 to the minus 2. Our next one, we're dealing with a real decimal point. No zeros to mess with. This is going to be 4 significant figures. I'm going to move our decimal point over 2, be 1.256 times 10 squared. 93 million. No decimal point. Trailing zeros will not count. We have two significant figures. To get this in scientific notation, we have to move this way 7 places. That's 10 to the 7th. Now this one is interesting. We have a decimal point, don't we? So that means that all of these zeros are real. This has 1, 2, 3, 4, 5, 6 significant figures. All of these have to go in the coefficient. We're going to move the decimal 1, 2, 3, 4 places. That's 10 to the 4th. And write it like that. And finally, leading zeros, 3 significant figures. Move our decimal 1, 2, 3, 4, 5, 6. And get 10 to the minus 6. Now, comes time to do an exam, right? I could give you a number and say how many significant figures. And I've done that many times. But that's boring. It's a boring question. And I thought one day, gee, I can write something more interesting. So I did this. Here are a bunch of numbers. Rearrange the stack in order of decreasing significant figures. Okay, we can do that. Leading zeros. Leading zeros don't count. Trailing zero does. This guy checks in with 2. Zeros between non-zero digits. 1, 2, 3, 4, 5. Decimal point, everybody's real. 1, 2, 3, 4, 5, 6, 7. No decimal point between real digits. This guy's a 4. Real decimal point. Trailing zeros, they all count. 1, 2, 3, 4, 5, 6, 7, 8. And finally, no decimal point, that's a 3. So, algorithm, it's going to be our 8. Then comes our 7. Then comes our 5. Then our 4, the 3, and the 2. That's a neat problem. Sadly, grading it for 500 people was impossible to do. And assigning partial credit, oh my goodness. I will never do that one again. But it was fun. There's a tutorial. This is everybody's favorite tutorial. Everybody's favorite because it's so simple. Once you grasp significant figures, it's so simple. No decimal, 3 significant figures. Decimal, count up everything. 1, 2, 3, 4, 5, 6, 7, 8. Scientific notation, don't even have to count. It's just 4. Leading zeros, they go away, trailing zero stays, that's a 2. Now, the other thing that people have trouble with is calculations. You do measurements and you're going to do calculations with them, right? That's why you do it. Addition and subtraction is the most unintuitive one. Let's say that we had these digits, these numbers, and we wanted to simply add them. Two measurements. The rule says you're looking for the fewest number of places after the decimal point. We feed this to our calculator, we get this. We look at our two numbers. This says 3 places. This says 1. The rule is you must round it to the fewest number. So this rounds to 7. 1 digit, 1 digit, 1 digit. If you're doing multiplication and division, it makes a little more sense. You have two numbers, two measurements. Your overall result can be no better than the worst, right? So you look to see which one has the fewest number of significant figures. So we're looking at these two and multiplying them. Feed them in the calculator, we get 0.294. 3 significant figures, 2 significant figures, we must round this to 2. And that's it. When you have the pleasure of taking the significant figure tutorial on Blackboard, you'll have these guys. So you do need to know these rules. Any questions? All right, we made it, guys. Remember the tutorials that apply to this chapter. Exponents, sig fig, decimal conversions, metric conversions, atomic configuration, that's protons. So that's 1, 2, 3, 4, 5, 25 points sitting out there. You must clean these before the first exam. Now don't put it off till then. You don't do it in real time, but this is 25 points sitting out there. Do it. Next Monday, we will look at concepts like orbitals, regions of space where electrons can be. The reason that we're going to do this at all is it makes understanding the concept of valence, that is bonding electrons, so much easier. All right. Have a good day. Wait. Wednesday. We have a Wednesday this week, don't we? Wednesday, we're going to go to lab. That's in D204 over that way. Wednesday, you actually don't need lab goggles. Only time. Bring them after that. Goggles. What we're going to do on Wednesday, very simply, is we're going to watch 3 short, like 5-6 minute